launch the Mobility City project and select this unique architectural space. And it's our headquarters with the aim of transforming into a national and international reference point for sustainable and innovation mobility. More than 500,000 people have visited Mobility City and over 300 activities have been held, including researches, conference, automotive awards, innovation days, and events with public and private companies and organizations. Last Thursday, we celebrate the third anniversary of Mobility City together with institutions and representatives from Aragonese industry. The goal of Mobility City promotes the values and challenges of the new mobility through conference, seminars, and professional events focused on the industrial and tertiary sectors, particularly within Aragon, while also fostering innovation and entrepreneurs among companies and startups across Spain. In addition, this venue includes a museum space dedicated to mobility and automotive culture. We are currently hosting an exhibition of Opel and his history. This 2026, we are looking forward to two new exhibitions that will continue bringing the passion for motors to the entire community. It's therefore especially meaningful to host the SSTAR project event in a space devoted to innovation and the improvement of the energy distribution networks. Thank you very much for your attention. I wish you a productive and successful event. Thank you. Jonathan?
Thank you, Jorge, for the welcome. Thanks to all attendees. Hi, Maria. Thanks to Mobility City again. Good morning, everyone, and the people who is connected online as well. It's a pleasure to gather here today for the final event of SSTAR project, a project that has represented, above all, a collective commitment to rethinking the role of power electronics in the future electricity system. The European energy transition is entering a decisive phase. The large-scale integration of renewable energy sources, the electrification of key sectors, and the increasing need for grid flexibility are placing significant pressure on existing electrical infrastructure. The challenge is no longer only to generate clean energy, but to manage it intelligently, efficiently, and safely. In this context, SSTAR was launched with a clear objective: to advance in the development of high-voltage solid-state transformers, capable of maximizing renewable energy penetration in distribution and transmission grids. Over 46 months of work under the Horizon Europe program, we have addressed this challenge through three main pillars: sustainability, technological innovation, and scalability. We have developed a bio-based dielectric fluid with reduced environmental impact, designed a high-voltage solid-state transformer module based on silicon-carbon technology and inductive power transfer, and created a decentralized control system prepared to operate in modular high-voltage configurations. All these developments have been validated in laboratory environments and supported by life cycle assessment, economic analysis, and roadmap toward a future deployment. Beyond the technical requirements and achievements, SSTAR stands as an example of European collaboration. Research centers, industry partners, and sustainability experts have worked together to transform advanced knowledge into concrete and applicable solutions. Today's agenda reflects this comprehensive approach. We will begin with our roundtable with a strategic discussion on moving from prototype to grid development, because innovation only reaches its full value when it enters the market and the energy system. Later, with the consortium, we will present the project's key technical, environmental, and exploitable results developed by all partners. This event does not simply mark the end of a project, but a transition from development to implementation, from research to future real impact on electricity system. I hope today's discussion are inspiring, generate meaningful dialogue, and open new opportunities for collaboration as we continue advancing toward a more flexible, digital, and climate-neutral European energy system. Thank you very much for being here today. Thank you.
Ahora. Okay, as we change the picture of the bottom of our panelists, now, as I said before, we are going to open our roundtable sessions titled From Solid-State Transformers Prototypes to Market and Grid Deployment, Powering a Sustainable Energy Transition. First, I would like to thank all panelists for accepting our invitation to be here in this final event of the SSTAR project. Thanks a lot for your effort, for being here with all of us. For the audience, let me introduce them to all attendees. Here, in my left, Samuel Borroy, Director of Electrical Systems at CET. Welcome, and thank you again. Javier Val, Director of Electrical Area at Altertech. Thank you. Thanks a lot for accepting the invitation. And finally, Jesus Alijarde, General Manager of Fiberseed. Thank you and welcome again. This is not the first time I see your face in European final event. Thanks a lot.
Thank you.
Okay, so I'm going to ask the first question for each of you. Okay, we are going to reply in this order. You are free of replying with the duration that you expect to complete your explanation. Okay. And the first question is for you, Samuel, and is based on your experience in European Grid and Power Electronics project at CET. What opportunities do these types of projects offer for technology development, and what are the main barriers today preventing solutions such as SSTs, solid-state transformers, from moving from the validation environment to real integration, and in this case for the STAR project in medium and high voltage grids?
Good question. Well, thank you very much. Do you hear me? Thank you very much for your invitation and for the introduction. Good morning to everyone. Thank you, Mobility City, for hosting this event. Thank you, all the SSTAR project consortium. And well, regarding the question, let's start by the opportunities. I think that it's clear that this type of European projects, in general, collaborative innovation projects they can and should act as technology accelerators. I think that they can help to dynamize and mature ideas. They allow the technologies that work correctly in simulations or in the first stage of the idea to be evolved, validated, improved and tested in laboratory environments and also in experimental pilot projects. Also, this type of projects helps to force these technologies to be confronted with the requirements of the industry and of the different stakeholders involved in the project. In this line, it also allows to define and test relevant use cases, considering the inputs of all the different participants in the consortium. And well, in general, it makes possible to establish these collaborative and validation environments within the consortium, integrating all these type of actors, no, in the project. And this is especially relevant in the moment that we are facing, as you mentioned in the introduction, no? Because this energy transition involves high penetration of renewable energies, power electronics in the networks, more complexity in the distribution and transmission networks, new actors such as prosumers, electrification, data centers, so on. So the evolution of technology is a key factor, no, to make possible these scenarios. And a little bit more specifically in this SSTAR project, I think that it helps what it provides the possibility to take some risks in the innovation, no? This project it has been able to develop prototypes of medium frequency transformer based on inductive power transfer. This type of projects also allows to define a common language for the, let's say, a pre-standardization, or at least some first stages that can pave the way for the subsequent processes for the validation or industrialization of the technology, and also, of course, another opportunities to strengthen the supply chains, the knowledge, the technology developments among the European members of the consortium, no? Which is also needed for this energy transition. And of course, there are barriers, as you mentioned, for going from this prototype scale to the industrialization, no? Opportunities of barriers, or let's say also challenges, no? More than barriers. We'll have technical barriers or technical challenges. In this case, for solid-state transformer, we will have always probably the comparison with the conventional transformer, which, well, as we know, is one of the more robust elements in the power system. But we will talk later, because I think that the comparison is not so direct. A solid-state transformer is not just a transformer. It offers more capabilities, more functionalities, so it's not so direct, the comparison. But anyway, there is still work to be done to guarantee the reliability, the thermal behavior, the insulation, and well, these things that at the end it are assumed for sure, for assets that you connect in the network, no? Another challenge is related with the grid integration. The grid will evolve in this energy transition with more elements, more power electronics, new grid codes, new requirements, and all the grids should evolve in that direction. The new control systems, more monitoring schemes, observability, and so on. So this is a parallel development that should happen, and it is happening, because there are a lot of projects related with all these technologies, but it will accompany, it will go with the evolution of the technologies such as solid-state transformer, no? And well, I'm just finishing. And also, there are challenges regarding with the, let's say, standardization or regulation, no? It is a lack of experience of this type of elements installed during a long time in the power system. So we still don't know questions about the real service life expectations and, well, thermal behavior and so on. So there is work to be done in order to have these certainties, to better understand the behavior in the long term, this type of solutions. And finally, of course, economic challenges, no? How it is going to be remunerated, especially for regulated business such as distribution, no? For example, how it is going to, this CAPEX and OPEX, which involve the integration of this type of element, how it's going to be recovered by the DSO in this case, or TSO, no? This is just the uncertainty of the market. What market signals will have to make worthy to install this element, apart from the functional benefits that later probably we will explain in the next interventions of the session today.
Samuel. You have been talking about technological barriers, regulatory, and adaptation to this kind of disruptive technology, okay, to the integration of real grids. And I think that it's crucial to have a good balance between the development of this kind of research, of this kind of technology, with the human factor. You have been talking to the commitment of the researchers and the consortium of this kind of European projects, and I think that is crucial. Without great commitment, collaboration, and coordination of this kind of technical task, especially with lower TRLs, yeah, we need to be accompanied with this kind of human factor in order to be in a good way, okay, and to reach the technical goals. Thank you, Samuel. Okay, and the first question for Javier is from the perspective of an energy cluster where Altertech belongs to. What role can emerging technologies such as SST play in industrial competitiveness and in positioning regions like Aragon, in this case, within the European energy transition?
Okay. Hello everybody. First of all, sorry for my English. If I don't get understood, you just tell me. So,
we are all Spaniards, so don't worry about that.
Okay, I'll do my best. So for industry, as my colleague said, the thing is about competitiveness. It's not only a transformer, it's like an intelligent transformer. So you can manage the interferences, you can, DC and AC can coexist in the place, and it's a better way to use it. It could be also an opportunity in Aragon to cap intelligent and engineering and retain after, because if we try here in Aragon, we can export to Spain and after also in Europe, and I think Aragon is a good lab to try, because we have production of renewable energies, and we have also starting to have a lot of demand in data cloud center, artificial intelligence, etc. So in these terms, we can do both sides of the story. And then in European positioning, as we said, we can try it here and export, so we can retain here the experience, the technology, and even also the maintenance after. Why not? So that's a little bit the idea.
Thanks a lot, Javier. Obviously, Circe, as coordinator, is located here in Zaragoza, in Aragon. We have a lot of opportunities with this kind of energy transition and sustainable projects with these European projects. But yeah, our experience is that we are really close to the European partners and European colleagues in order to distribute this kind of knowledge that we gain with these projects with future deployment and future projects, collaborative projects, in this case together to the European Commission, that give the opportunity to finance this kind of research projects that are crucial in order to go ahead with the 2030 objectives especially. Thanks a lot, Javier. And Jesus, your turn. Your question is, when we talk about advanced technologies for electrical grids, such as SST, how can we ensure that technological innovation is accompanied by real benefits in terms of environmental sustainability and a just energy transition?
Okay, first of all, thank you very much for inviting my company, invite me. It's a little bit strange because my company is a sustainability consultancy company. So we are we manage environmental and social issues around the energy projects or infrastructure projects, or big projects. So it's a little bit strange because it's a very technical question, the solid state transformer, with the idea of environmental or social issues around the local communities. But what I read about the project, I'm very happy because the project, all of you introduce the environmental issues from the beginning of the research project. So I'm very happy about that. And also, I think you have introduced in the project the circular economy principles to design the new infrastructure, infrastructure of transformers. So, in my opinion, I think that the project, the idea or the focus of the project to achieve a new transformer based on a different technology that impact directly in the environmental and the circular economy production of the infrastructure that are now built. I think it's a good idea, it's a good focus, and I think I'm very happy about that. But added to that, as the other companies of the roundtable has told, the new infrastructures to introduce with stability the renewable energy into the electrical system, I think the investment needed to update the infrastructure that are now landed is a very high, is a deep, high opportunity to Aragon, because as Javier has told and also Samuel, Aragon is a place that we have a lot of produce of renewable energy. We can produce a higher amount of renewable energy, and we need to introduce with all the safety rules of the safety rules or technical issues for create a electricity system safety and competitive for all the people that we are living in Aragon or in Spain. And also, most of that substation now in Aragon are landed in local communities, in rural areas. So it's a important opportunity, a high opportunity to invest in the population areas and create local employees, local impact, local investment, and increase the economical opportunities in the areas. Also, the part of the environmental respect, the circular economy principles of the substation, of the solid states, and I think the next step is how to manage the local community capabilities to create shared value around the new investment of the solid state substation in the local communities in the rural areas.
Okay, Jesus, thanks a lot for your reply. It's not as strange, your intervention here, because, as you said, we should keep always technology and sustainability in the same link, okay? So it's crucial to develop technology in this kind of projects by considering the sustainability as one of the crucial key points in order to create and develop in this case. And this kind of investment, in this case from the European Commission for the research projects, it's, the key point here is clear, okay? It's from one hand, the technology, and on the other, sustainability. My colleagues later on will explain during the results of the project the work carried out during these 46 months. And all you will see that they do not talk about only technology and SSTs, but also a right roadmap onto the market and link to the sustainability all time. Okay, so it's really crucial. Thanks, Jesus. Okay, it has been the first round of questions, and then we are going to continue with the second question for each of them. Okay, and Samuel, again, for you, your second question is within the framework of the project, of SSTAR project, what role do technology centers, like CIRCE in this case, play in reducing technological risk and making these innovative solutions attractive to grid operators, industry, or something that is crucial nowadays, data centers, artificial intelligence operators as well?
Okay, well, within SSTAR project framework and in general within technology or innovation development projects, I think that we can summarize the role of technology center as that we try to turn innovative ideas into confidence, no? The confidence that the industry or the end users of these technology ideas need to consider that they are worthy to implement in their business, no? And of course, specifically, it means to help in reducing or mitigating the technical risk or challenges that I have mentioned before, no? So for that, what does a technology center provides? Well, capabilities to design, model, prototype, test, validate these ideas, no? To take from them and to act as a bridge between research and implementation in the industry, no? So regarding technical risk, well, we provide this design and engineering capability and also the test infrastructure and methodologies to validate all this technical development. And also in this project specifically, it's key how we manage the scalability of the solutions, no? Because at the end, we are talking of implementing this type of solutions in distribution and even transmission networks. We have to assure the scalability. So regarding this, technology centers, such as CIRCE in this case, we have developed these core elements for this scalability process, which is the medium frequency transformer based on IPT and also the control strategy and validated in hardware in the loop methodologies. And well, at the end, this stage of the bidirectional SiC, silicon carbide based DC-DC concept, no? Also, we can help in reducing the integration risk, which is to understand how this element should interact and should be integrated in the network or in the data center or in the element where it should operate, no? And for this, we have, as mentioned before, the hardware in the loop and power hardware in the loop environment in which we can reproduce or emulate any circumstance, any situation that the solid-state transformer should or would suffer in the real life in order to check the behavior and to improve the design and to evolve the development to assure a correct integration with the real world in which it is going to be installed, no? Of course, including the interoperability with the different elements, communications, and so on. And regarding the scalability, I think that one of the main developments of the project, we will see later in more detail, is this decentralized control for a 30-module cascade edge bridge, which has been tested using the hardware in the loop, and it helps to reduce the barrier for the scalability of having a centralized control system, which could be a bottleneck for this scalability. No? This decentralized scheme allows scalability. No? Also, we can help in reducing risk related with the adoption of the technology. So we can understand both sides, the specific characteristics of the element that we are developing, in this case, the SST, and also the requirements of the final user, so as to translate and to understand which is which of the capabilities of the technology which can be used by the user, no? And therefore to ground these use cases to demonstrate that, as I mentioned at the beginning, then SST is not just a transformer, but an intelligent interface which can allow more things that what a conventional transformer can offer, no? So we can define the use cases which ensure the AC/DC integration, improve voltage and power flow control, and also the power quality capabilities, no? But which can offer the solid-state transformer. So at the end, this is, as I said, this traduction between specifications and use cases which can be or which can take advantage of these advanced functionalities.
Okay, Samuel, many thanks. Yeah, really interesting. Usually, many people only have visibility of this kind of technology once they are directly in the market, okay, in our daily life. But behind that, there are a lot of research for many years, and this kind of projects makes possible this kind of integration into real market, okay, from validation, and the good path from research to market is that one, okay, to reduce risk from the initial research stages in order to create lesson learned and how to integrate this kind of crucial technology in our daily lives, okay? Thanks. Okay, let's continue with Javier. Question 2, what regulatory, market or public-private collaboration conditions do you consider key for innovations developed in European projects to truly reach the industrial fabric?
Okay, thank you. I would like to structure in in 4 parts. The first part, I would like to talk about regulatory framework. It can't be only private investment. It must be also public investment and cooperate to achieve the goal or the new goal about the grid, because we have problems now that before we haven't. So we must solve it soon, if it's possible. Also, after, it's not only about to build it. We need to standardize and certificate the SAEs, because it's not only the way that we are going to build in the first tries. Is we need to know how to certificate, how to maintain, how to many different things. So it must be standardized. Also, the other thing I would like to talk about is about the risk sharing, because if we don't incentivize this kind of essays with the private companies, we cannot know if it's going to work or for a better way in the grid. So the risk must be separate and must be also maybe public information once is tried, public information to motivate other companies to install this kind of transformer. And then also the problem that we have in Europe nowadays, we need to relate it about manufacturing. So we need to, if we can, to reindustrialize and do it here. And that's, I think, the keys to my mind.
Obviously, all these kind of requirements must be aligned, both from the technical point of view and regulatory and market, obviously, that both must be integrated in order to fulfill not only the technical objectives, the European climate conditions, but also from the market. We are always talking, and the core of this roundtable is from prototype to real market, okay? And that's crucial to be aligned with and to have this knowledge clear about both requirements from a technological point of view and from regulatory in order to have all this kind of standardization established from the initial stages of this kind of research projects. Okay, thanks. And second question for Jesus. In research projects such as SSTAR, what value do tools like life cycle analysis or socioeconomic assessment bring to guiding technological and deployment decisions, in this case for medium and high voltage grids?
Well, obviously, I'm going to give my opinion. From my point of view, you must introduce the life cycle analysis or the carbon footprint or the water footprint in any new technologies. And I think the sound is not good. Yep. Okay. So you must introduce those kind of analysis into the new researching and new innovation, and also in the companies that now are producing products, because we are moving forward to a world with a lower amount of resources, a lower water supplies. So as human beings, we must have a very deep commitment with the future human beings. So now, in our present, the life that we have to live, we need to ensure that future. So a new investment, a new research project, a new innovation in all the chains or the production chains, no? You must to focus a little amount of energy into the life cycle of the product of what you want to introduce in the market. So now it's not mandatory. I think there are only 2 or 3 points or regulatory points that you have to give the life cycle analysis. But I think the future is all the products must to give that information to all the customers or the clients or to the market. So as I told at the beginning, I'm very happy because your project introduced that analysis from the beginning, and you are in a very. I'm not sure if you are far to the market nowadays. So introduce that idea in a very early stage, give you, in my opinion, a competitive advantage with other technologies or with other projects that want to introduce a technical or economical improvement into the high voltage infrastructure system. So, well, I think, summarize my opinion, I think in any case in our economy, you have to introduce you must introduce the life cycle analysis, the carbon footprint analysis, and also the water footprint analysis to ensure that we are going to live in the future of the Earth.
Okay, Jesus, thanks a lot. I think that you're right. Okay.
Well, thank you.
Yeah.
It's only my opinion.
Yeah, no.
There are a lot of people.
You are, in fact, as you will see, SSTAR project at the European projects create this kind of analysis, LCA, LCC, in order to bring this kind of sustainability solutions to make fulfill the objectives and better decision in this kind of projects to put in a position with better competitiveness, as you know, in the market. Okay, I think that is crucial. Thanks a lot for this second round. And finally, before closing the round table, I'm going to ask you only one last question. This question is common for all of you, okay? So we are going to reply, you are going to reply in the same order, okay? And the question common to all of you is looking toward 2030 and considering the evolution of European electrical grids, what needs to happen at the technological, regulatory, or market level for solutions such as SSTs to move from being a promising innovation to becoming a common element to the power system and emerging applications such as data centers or artificial intelligence is something that we are continuously talking about. Samuel?
Okay, so you asking for the crystal ball, no? Well, I think that if we think in 2030, the question is not if there is going to be high penetration of power electronics in the network, because I think that it is already increasing in distribution and transmission network and also in the generation side, but it's at what speed and what impact and so on, no? And I think that for solid state transformer in this context, probably it will be room, but it's true that some questions has to be fulfilled, no, regarding technical and regulatory and economic aspects. Regarding our technology level, I think that we have in the previous questions talk about the reliability of the element comparing with the conventional transformer. It is obviously a need to guarantee the real implementation in the power system. But also I think that it's relevant that the first implementations, the first use cases, real use cases are, as mentioned just already before, in use cases where the main benefits of this technology are relevant, no? I am talking about the voltage control. Solid state transformer allows for a better control of the voltage in the distribution network, no? So this helps to increase the hosting capacity of renewable of distributed generation in the network. Also can help to reduce voltage problems, which can bring the high electrification of the networks. Also help to improve power quality, acting as a filter for harmonics and other power quality issues. And I think that which is the main or the most tangible advantage is to act as an efficient and controlled bridge between the AC and DC elements integration. No? So in this future with a more or high deployment of PV in distribution networks, batteries, electric vehicle charging stations, this DC bus can help to integrate all these elements, no? And in a better controlled way. So I think that these use cases, it's important to be implemented to take advantage of these benefits of the technology. No? We have some examples in CET, for example, in Tigon project, which we can say that is the older brother, no, of SSTAR project. We finished some months ago. We integrated a microgrid in DC, and thanks to another solution of solid state transformer, we allow it allowed to save up to 25% of losses, reduce up to 33% of copper compared to a conventional DC network. No? So I think that this is one of the use cases that should be potential to improve or to foster the implementation of the solid state transformer. And on the other hand, we have data centers, which of course is one of the, well, not new because they are already here, no? But one of the facilities which is going to be increased, no? At European level and worldwide. So for this type of installation, SST can be, of course, a useful device because it provides functional integration of different elements, such as transformer, UPS, conversion phase, energy management, and so on, which with conventional, let's say, conventional technology, it involves different type of elements. And with a solid-state transformer, it can be a more compact and with a high degree of controllability solution with several advantages. No? We deliver DC to this common bus where the different elements of the data center can be connected and controlled. The power quality capabilities that I have mentioned before is quite relevant for this type of consumption because data centers have a very critical and sensitive elements which needs this power quality. So this type of first use cases would be, I think that it would be key factor to foster the implementation. In addition, of course, to ensure the reliability, the scalability that we have been working in this project, and also, of course, cybersecurity as any element which are connected to the network and so on. And apart from these technology factors, as I mentioned before, the grid codes will evolve. So of course, the solid-state transformer control elements should be appropriate for these new grid codes, which I think that is absolutely feasible because it is question of including control capabilities with is part of the nature of the solid-state transformer. And the last point also mentioned at the beginning is the economic factor, no? The market signals which make profitable or worthy this type of solution. I have mentioned before these savings in losses and so on, but also the regulatory aspects, especially for distribution networks, which are regulated business. They will have to also to evolve to make attractive the investment of these new technologies.
Okay, thank you, Samuel. You have mentioned words like control, digitalization, reliability, better quality, better integration. This concept is going to be repeated probably more times during the presentation of my colleagues because those are one of the core elements of this project, of the STAR projects. And obviously, we directly think in the real or direct application, the first application in the integration in the electrical grids, but obviously the benefits must be wider. Okay, in this case, with this kind of grid, more flexible, intelligent, we will be able to reduce risk. Economic assessment as well will be integrated better and lower consumption. So the benefits are really, really crucial and not only to think directly to the transmission grid. So we have, fortunately, a lot of applications to be integrated this kind of technology. Thanks. Please, Javier.
As the technical talking is after, I'm going to be quite short about the ideas I would like to talk. So the first stage, it would be testing, but testing not only the performance, that testing in a real grid or real says, as my colleague talked, the voltage variations, interferences, and these kind of things should be tested, not only the performance of the transformer. And then, as I talked before, and my colleagues also, we need to regulate and incentivize these uses, because if not, we are not going to arrive to 2030 with this kind of solutions. And then one is incentivize and test it in laboratory. We need to find partners in real grid, we can say, and start to using it in strategical points that must be useful. Not everywhere, but maybe in the places that the demand is high or the variation of the grid are significant. So we can try in a real way and see how it longs, how is the maintenance, and how is everything. But we need to start trying in a real way.
Okay, thanks. Thanks, Javier. Yeah, obviously, during the research stages of this kind of projects, we have to collect this kind of lesson learned, okay, in order to reduce risk. And if we identify some failure, those failures must be identified during the research process of this project and not in the real market. That's the key element of this kind of research, okay, to learn about this kind of technology and to try, based on previous knowledge or even innovative knowledge or crazy ideas, even that's something that is crucial as well from the research point of view, and then to learn, to identify where we have failure in order to identify solutions, technological solutions, from another point, okay, from the regulatory standardization or wherever, in order to step by step create this kind of technology completely, fully ready, okay, for a real roadmap until the real market, okay. Thanks. Jesus?
Well, if I answer specifically the question with the solid-state transformer, I think I'm not going to give you deeper or better explanation that Samuel or Javier has done. I think technical, I think economical and also regulatory issues could create the best conditions to deploy faster the solid-state transformer. Because if you are more economic than the technology that are now, you are going to deploy faster than if you are more expensive. It's an obviously low of economy. But I want to put my mind upper and answer you in a general idea, because in my opinion, this kind of projects or this kind of technologies are answering the question of create a new world, a new society, a new way of live in the world. So the just transition, the energy transition, the new economy, the new technology, the new way that all the people link with the other parts of the society need aligned idea. All the people in the European Union or in a state or in a community must to share the same main objectives. Without that, it's impossible to ensure a faster deployment about the things, the technology that we need to answer the future that we are creating. So, in my opinion, put my mind as upper as I can, we need a deep, a shared commitment about what kind of world we are creating today in the European Union, in the world, in our state, in our community. Because if all the people have the same commitment about we need a lot of renewable energy, as much renewable energy that we can, I'm sure that we need solid-state transformer faster. We need maybe in the next year or in the next 2 years, although we don't have now the technology. I'm sure that all the resources are going to come to the research center, to the projects, to the producers, to answer the demand that the market need in the next 2 years. So, well, I think the big commitment about how world we want and how energy system we need in 2030 or 2035. With that commitment, it could be easier as a solid-state transformer or any new technology that answer this demand.
Thanks for giving your view. Yeah. Again, we have back. We came back to the human factor that I think that is crucial. Okay, not only from the technical point of view, and we have, as you said, we need to be in the same page. Okay, to be aligned with these kind of objectives at European level. Okay, in order to fulfill the objectives that comes from an initial investment to the final deployment of this kind of disruptive technology. Thanks a lot for this fruitful discussion in this roundtable. It has been great to hear different perspectives because they come from different views and different experiences from different companies with different expertise. Okay, so it has been great. The key point here with this roundtable was not to put together people expert in SSTs, but on the contrary, to put on the table that these kind of technologies, how can these kind of technologies can improve our daily lives and to put on the table the wide applications that we can have and where is the good path in order to move from prototype to the integration of the real grids and real market. Okay, thanks a lot. I think that we are on time. There was no organized questions for this, but it's not necessary to ask any question. But if someone here from the audience wants to say something in terms of some reflection directly related to the discussions that we have exchanged here with our panelists, go ahead. So you are free to say something if you want to. And otherwise, we will go directly to the coffee break before continuing with the project's results. Anything to comment here? No? Okay, that's because you have commented everything clear, 100 clear, okay, that you have commented and discussed here. Thanks a lot again. Okay, thank you. As I said, and based on the agenda, we have around 30 minutes of coffee break. Because we are on time, we can be around 35 minutes of coffee break, okay? And then we will go on with my colleagues of the project, okay? And we will show the work carried out during these last years. Thanks a lot and enjoy your coffee break. Thank you.
here in these chairs. And once you indicate a turn for speaking, you stand up, okay? ¿Dónde está Stefano? Okay, so after the coffee break, so we had the opportunity to deeply breathe after this break and the previous discussion on our roundtable. We will continue with now the results of our project, SSTAR project. So first, let me give a project overview presentation, okay, of the project from as I said, an overview of the project with general information, and later on my colleagues from the consortium will give you more details, okay, about the work, okay, that they have carried out for these years. Stefano, please. Yeah. Okay, great. We have completed the, the chairs. Yeah, no, don't worry. I have to make the introduction first. Okay, so SSTAR, this is the SSTAR in figures. The main topic is to research about an innovative solid-state transformer for maximizing renewable energy penetration, energy distribution. And in this case, and the main technical challenge is to make an application for high voltage transmission grids instead of low voltage. This is a project of research and innovation action with a total budget around 0.5 million euros, with a total duration of 46 months. We have been working since May of 2022, and the official closing of the project is on 28th of February 2026. So with this event, we are almost approaching to the final step of the project. We have been coordinated this project from CET with 6 partners, CERT, RINA, EFASEC, ICONS and Novamod, 6 different partners from 4 different European countries. We have been commenting this previously during our roundtable, the key point of the great collaborative and commitment among the partners with this kind of European projects, and this is the case, okay? With this graph, you can see the links between the different work packages where we have been carried out, and the commitment from different perspectives and expertise from research centers, companies, technology developers, and experts in sustainability and dissemination and replication. So as you can see in this graph, this collaborative work is essential in order to fulfill all the technical objectives of the project. And this is the main goals, okay? If we need to summarize the project, we need to say that SSTAR bonds in order to overcome the technical barriers that currently the conventional solid-state transformer has in the current market, and we need to tackle this kind of technological barriers. We have been working with 3 main research and innovation lines. We have developed a bio-based electric fluid to increase the insulation voltage of SST modules. My colleague Stefano from Novamont will give more details about their work at Novamont. We have designed an innovative SST module, including the IPT, bidirectional inductive power transfer for medium voltage application. My colleague Eduardo from CET will give the speech with more technical details about this. And a decentralized cascade bridge control converter in order to scale up the number of modules for these high voltage connection applications. That will be explained as well for my colleague Eduardo. And with these innovative lines, we have developed a testing campaign in 2 laboratories in Portugal and in Spain in order to validate from the research stage, from TRL 4, in order to have 35 test beds of the project. And obviously, we have been talking about this topic as well during the roundtable. It's crucial to perform and to assess a life cycle assessment framework, quantifying environmental, economic, and social benefits of this kind of technology. And we have created a right roadmap in order to scale up this TRL, in order to identify with this kind which requirements are crucial in order to implement this kind of technology in the market. I'm going to reproduce a video that summarizes very well
the ongoing energy transition towards a decarbonized economy is profoundly changing the infrastructure of the power grids worldwide. The current
So we're going to try to fix the issue because I would like to avoid some damage in your neck. I think that it works.
The ongoing energy transition towards a decarbonized economy is profoundly changing the infrastructure of the power grids worldwide. The current technologies like high-power transformers are not fully prepared to face these challenges. Only solid-state transformers, SSTs, have shown a potential capacity to extend the typical functionalities of a regular transformer. This system, however, is still not mature enough to operate at high frequency. STAR is an EU project that aims to increase the operational voltage level of SSTs to enlarge their applications within the energy power sector, while improving their performance in a cost-effective and sustainable way. To reach this goal, the STAR consortium will develop 1. A bio-based dielectric fluid, able to increase the SST module's insulation, with a huge impact on carbon dioxide savings. 2. A new SST module with a bidirectional inductive power transfer system, IPT, able to increase the individual voltage and switching frequency. 3. A decentralized control cascade H-bridge converter, CHB, to scale up the number of modules in a single SST device. All these innovations will be validated in 2 certified testbeds in Spain and Portugal. Learn more about how STAR can help the energy sector becoming greener and more efficient.
Okay, as explained in the video, we have carried out several test beds, both in Spain and Portugal, at FACEC facilities and in CET, with different objectives, in order to validate all these kind of critical aspects, to create several and collect lessons learned in order to go ahead with this kind of solutions. And we have carried out several tests based on losses, efficiency, performance, dielectric strength, and so on, that will be later on explained by my colleagues. And this is the expected impacts, not only from the technological point of view, in terms of the energy, to maximize the penetration of renewable energy, ensuring the correct and safe operation of the grid. The environment, obviously, we have performed LCA and LCC analysis to quantify the environmental benefits and the solutions proposed from the initial stages of the project. Obviously, from the point of view of technology and engineering, with our SST design and the test beds that we have developed in our laboratories. And obviously, there is not only impacts from the point of view of technology, engineering, and environmental, but also the bioeconomy is one of the expected impacts of this project, the integration of bioeconomy practices in the energy sector and socioeconomy. So we have assessed not only the environmental impact, but also the life cycle, economic and social aspects. And this kind of expected impact together, that's the main goal in order to move, as we have commented with the title of the roundtable, to move from the prototype to real applications. And with this, I'm going to give the floor to my colleagues. In this case, we are going to start first with my colleague Stefano from Novamont. Please.
Okay. Good morning, everyone. I'm Stefano Stefanetti. Today I'm representing Novamont, but also I'm speaking on behalf of Angela, the project manager from Novamont side of SSTAR project. Okay. Yes, exactly. Before we start, I would like to thank our project partner, CERT, and RINA for their essential work during the project. Okay, so let's dive into the major achieved results we obtained regarding the sustainable bio-based dielectric fluid. Looking at the main objectives of the work, we had three main goals. The first one was the development of a bio-based and biodegradable dielectric fluid, specifically designed to enhance the SSTAR module performance. And you know, the dielectric fluids has to provide two main functions. The first one, electrical insulation, in order to prevent discharges in the system, and then thermal dissipation to provide efficient heat removal for system stability, and also to avoid system damage. The second was the successful production at pilot scale level, ensuring quantity and quality required for the final testing in the high voltage solid state transformer. And third, the establishment of the technical parameters and health and environment criteria for the application. So the logic and purpose behind this was based on two main pillars. First one, sustainability and safety. We focus on the replacement of the fossil-based manure oil with an innovative circular bio-based alternative that could also provide an intrinsic biodegradability and enhanced operational safety. And second, we focus on the understanding of the fluid behavior through plasma modeling and while ensuring operational safety. I don't know what happened. Jonathan? Okay. So, looking at the key activities we have developed during the project, the first one was for sure the selection optimization. We performed an extensive research in order to find, study, define, and screen the dielectric fluids based on two main families. First one, bio-based ester, and the other, natural vegetable oil. Second, what was the health, safety, environment study and risk assessment performed with RINA through HEDSIT and HAZOP analysis in order to define the safety measures for the application. Third, the numerical analysis and plasma modeling with CERT in order to determine the fluid's influence in preventing corona breakdown. And finally, the pilot scale achievement, ensuring that the biobase meets all the technical requirements for the final application. In this slide, we can see the main result achieved during the project. First one was regarding the fluid optimization, the development of two high-performance bio-based fluids of both family, vegetable oil and ester-based oil, both tailored for high-volt solid-state transformed. We decided to produce and to deliver the one from vegetable oil family because it shows more consistency result moving from lab to pilot scale. Another important milestone is that the fluid fully meets all the requirements according to the relevant reference international standard. And finally, we finalized the HSC risk profile and the numerical confirmation of corona discharges prevention. Looking at the main impacts we had, we could divide in three major benefits. From a safety point of view, the fluid has a low flammability and a low risk of ignition that could be essential for reducing fire risk in wind turbines. This could be a very specific added value, a game changer, I would say, especially in hard-to-reach offshore or remote location. Second, from an environmental point of view, the fluid has a bio-based origin, a very high biodegradability, and this could limit the damages caused by accidental spill into the environment. Moreover, considering its superior thermal stability and dielectric strength in general, it could allow for a more compact design. And you know, in LCA, less is more. Less material means a better environmental performance. From equipment protection point of view, finally, the fluid has a high tolerance to humidity and water. This could help to prevent the damages of internal parts sensitive to this aspect, like graph paper, copper, and could extend the equipment life and reduce the maintenance and the cost associated, replacement, etc. The success indicators confirm the excellence of the work we have done. From a thermal safety point of view, the fire point of the oil exceeds standard by 10% and flash point by 4%. From an environmental performance point of view, the fluid has an intrinsic biodegradability very, very high, 72% in 28 days. Finally, this result was possible thanks to a very in-depth study on the formulation of the additive package that led to obtain a fluid that is not only an alternative, like for lye substitution, but it outperformed the mineral oil from a performance, like we see in this slide, safety and technological point of view. Finally, what we are learning, where we are going, yes, the most important thing that I would like to underline is that this high-tech goal was possible thanks to the successful cooperation between different entities, different companies, in this case, chemistry, safety, and modeling, and then our research innovation is the key to overcome the current technological limits and also to face all the challenges posed by the inevitable green transition. So what's about the future work lines? We have demonstrated that this technology could be ready for further upscale, moving from the current TRL 7 to upper TRL scale. So there is the potential to support a local supply chain, European supply chain, and a sustainable dielectric fluid niches in Europe. And this could result in the possibility of creation of new employment opportunities in manufacturing, specialized maintenance, technicians, and green services related to this area. This was my last slide. Thank you very much for your attention.
Okay.
Hi, everyone. Thank you for coming, to all the partners also for coming to this final event of the STAR project. My name is Eduardo Garcia. I work as a researcher in CIRCE. I'm also the technical coordinator of this STAR project with Jonathan. So I'm going to show you some of the developments done in this STAR project, but first let me deep into what is a solid-state transformer in order to understand what we have developed inside of this project. So a solid-state transformer, the definition of a solid-state transformer is a power electronic converter that provides isolation between a medium voltage to a lower voltage system using a medium frequency transformer. So the solid-state transformer are based on a transformer that works at higher frequency than the frequency of the grid, normally usually in the range of kilohertz, and to manage the power through this transformer, we need power electronic equipment in order to transfer the energy. So it means that this transformer, if we are looking to the main characteristics of these SSTs, is that this transformer, due to this high frequency, has a reduced size because more or less the volume of the transformer decreases linearly with the frequency. So if we increase the frequency operation 10 times, we mostly decrease the size of and the volume of the transformer 10 times. So it's an increment it's a reduced size of the transformer, but these power electronics are based on transistor, in this case, on this development on silicon carbide transistors. But these transistors are in the range, they operate lower than 10 kilovolts in the market. There are no transistors more than 10 kilovolts operating in the market. So if we want to go to medium voltage grids, that is one of the requirements of this SST, we need to do something regarding that. So the SST has the ability to serialize the converters in order to reach the desired voltage that is needed for every application. But also it is also possible to parallelize these SSTs in order to reach the desired current, the desired power. So it is like a Lego piece that you can put, that you can serialize in order to increase the voltage, or parallelize in order to reach the desired power, which give us a lot of flexibility to adapt to any necessity of voltage or current or power. So give us a lot of flexibility, but if we also connect, for example, at one side or to the other side, AC-DC converters to connect to the electric grid, we can also fit to any voltage or any grid frequency, which allow us a lot of possibilities in terms of controllability, because we can manage every time the power and the frequency operation of the system. So give us a lot of advantages in comparison with LFT solution, low frequency transformer. So if we are focused on this scheme idea of an SST in this STAR project, this is the SST, the idea of the SST in this STAR project, we have focus on two main developments. One is this converter, that the development of the medium frequency transformer, the MFT, with the converters. It's a DC-DC converter to manage energy, but with higher isolation, and also the connection to these medium voltage AC grids. So if we focus now on the first development, and we want to design this medium frequency transformer for this high voltage application, and we go with a classic coupling of this transformer. We have a thermal and isolation voltage trade-off, because if we want to increase the voltage isolation between primary and secondary, we need to increase the isolation material voltage between these two elements. But this increment in the material becomes harder the heat dissipation of the transformer. And it is a problem because this transformer operates, remember, at higher frequency in the range of kilohertz. So generate a lot of thermal issues when we want to reach this higher voltage application. So the solution that we have applied in this STAR project is to try to decouple the isolation voltage with the thermal management of this medium frequency transformer, using as a medium frequency transformer using inductive power transfer coupling between primary and secondary, because with that we can increase the thickness of the isolation material between primary and secondary in order to reach the desired isolation between primary and secondary without compromising the thermal management of each side. This is a pattern from CET that we have developed this SST module inside of the STAR project with 72.5 kilovolts of isolation between primary and secondary, with a DC bus voltage of 1500 volts and a peak power of 75 kilowatts of transmission, bidirectional transmission. So, as a main activities developed inside of the project is the multi-domain optimization across electromagnetic design, mechanical design, thermal design of this IPT, and also the design, development, and manufacture of the power electronic hardware, and also the development of the software control of this SST. All of it in one entire cycle of design, which is due to the time and budget restriction, we needed to do it in one design cycle to check these final objectives. So, as a main result, we have designed a the IPT is based on a double D design that reduces the losses in comparison with rectangular typical coils, and this is the first time that it has been used, this design for SST application. We have applied a 50 millimeters of separation between primary and secondary in order to reach the required isolation between primary and secondary. We have designed, developed, and manufactured this power electronic converter based on a 3-level neutral point clamp type converter, of course with the possibility of serialize and parallelize in order to reach the requirements of the project. All of this design has been included in a paper that we published the last year that include all the design parameters that you can check it there. And as an impact, is mainly the impact of this project is this design of this medium frequency transformer for medium and high voltage application, thanks to this IPT solution, which enable the high voltage galvanic isolation, shifting the heat dissipation from the voltage interface. Okay? Also with modular scalability for flexible power and voltage rating that enables new use cases. Mainly, I think, the integration in medium voltage and high voltage DC generation and consumption with renewable energy, for example, EV megawatt charging hub or large data centers consumption. The second development, main development in this STAR project is the connection, the medium voltage connection with the AC grid. This control of this serialized converter are mainly based on a central converter that, remember that in order to reach this medium voltage AC, you need to serialize several number of elements, 30, 40, 50 elements, or even more. So to control all of them with one only central controller, it's a bottleneck. It's a trade-off between scaling these higher voltages and maintaining central controllability. There is a bottleneck there. So, as an objective of the project, we have developed this decentralized control for cascade H-bridge converter, CHP. That is, it's how it looks like a CHP controller. It's our H-bridge module serialized in order to reach the desired voltage in AC. And we have developed a control that is included and managed only one module per branch. So there is no central bottleneck in the control of all these CHP controllers. And we have emulate the behavior of the total CHP controller of one branch in a real-time simulator doing a mock-up of 30 modules serialized. As a main activities developed in the project, we have first developed a simulation in order to test and validate the centralized control algorithm in Simulink. We have also developed the hardware-in-the-loop test bench in order to test the implementation of the controller, and of course, the implementation in a DSP of the real-time control with the communication, with the state matching, with the PWM generation, with the error management, all of the needs that these control developments for this high voltage application for AC needs for that. So as a main result, we have achieved a control of the current that can work in the 4 quadrants. We can consume active power, but also we can deliver reactive or even give power to the grid. So we can, this control can operate in 4 quadrants behavior, and the main impact of this development is it gives us the scalability to go for higher voltage application, because there are no bottlenecks, there are no computational limitation that offers you the centralized element. Also, the algorithm development balance the serialized converter, all of them with a daisy chain communication, which reduce the isolation needed between the elements, excepting the first communication module with the last one, which needs to handle this isolation. Increase also the dynamic response, because the processing of the CPU or the DSP are shared. Higher controllability, we can manage voltage and reactive power for giving support to the grid. And increase, all of them increase the range of the cases that we can use it, because it can be used for medium voltage to high voltage application. It can be used for more with developments with higher TRL that are very close to the market, like, for example, medium voltage application like data centers, or integration of renewable into the medium voltage grid. So as a lesson learned in the project, combining these two developments, in medium and high voltage, medium frequency transformer development, usually the isolation distance are often dictate the overall size more than the power electronic itself, because you need to have a bigger distance to keep the isolation between the modules, and also the bushing needed to handle this voltage are, in this case, even larger than the transformer itself. So as a possible solution, or possible ways to track this issue is to, for example, to develop only one MFT per branch, using a modular multi-level converter for high or medium voltage application, but for DC-DC conversion, or instead of using oil, try to integrate the power electronic with the MFT in one piece, so you can enable multiple MFTs per branch with only two bushing per branch of the power electronic equipment. And last, in case of the CHP, the series connection forms a chain. So if one link fails, if one link fails, can impact the operation of the entire branch. We have had a lot of problems with the serialization of the converters due to the noise and operation of module. It has been a challenge in the project. So thank you for hearing me.
Hello, everyone. Thank you for being here today. I'm Andrea Soto from FSEC, and today I will present an overview of our work on prototyping. Huh? Okay. On prototyping, testing, and validation at TRL 4 within the STAR project. So our focus was build and test the 2 solid-state prototypes in order to validate the 3 key components of the project: the bio-based dielectric fluid, the bidirectional inductive power, and the decentralized DHV controller converter. So here is where the dream finally became to the reality. We built 2 different prototypes in order to validate different technologies proposed within the project. Prototype 1 was used to validate the inductance power transformer design and the VHV controller. What happened? Okay. Controller system. The prototype has 2 main components. The first one is the IPT with the light wire coils and the ferrite electromagnetic screens, and the other one is the power electronics modules. The prototype 2 was designed to assess the thermal, chemical, and the electric behavior of the bio-based fluid. It has the fluid, the tank, the high voltage and the low voltage bushings, and the coils. Here you can see the assembly of the VHV converter. We mount full rack assembly with 30 control boards in a single branch of the VHV converter, integrated with the real-time simulator. So we have here 5 trays, each one hosting 6 control boards. In this setup, the VHV model runs with time steps of a few hundred nanoseconds with no central control. All the boards communicate in a closed loop daisy chain, and with the current control algorithm runs at 24 kilohertz with synchronous interboard communication. As main results of the prototype 1, you can see here the full assembly on the prototype, and on the graphs you can see that we achieve the nominal operation conditions. Moving for the results on prototype 2 and to evaluate the chemical performance of the fluid, we check the fluid before filling the prototype and after all the full test campaign. All the chemical and the AGA analysis confirmed that the fluid remains stable without signs of degradation or contamination, and fully compliant with the IC standards. We also evaluate the thermal performance by applying a controlled Joule heating on the windings, and across all the heating tests, the fluid remains stable, thermally stable, and the steady state temperature rise were consistent with the theoretical thermal models. For the dielectric performance of the fluid, we carried out these dielectric test sequences that you can hear in the table, starting and ending with the half-wave impulse test and performing full-wave lighting impulse test in between. Through all these tests, the insulation system remained stable. All the key parameters stayed in the expected and expected range. No signs of waveform distortion of abnormal behavior, and the results confirm that the fluid has a good performance, the electrical performance under fast transient over voltage conditions. To test the CHV control converter, we test 28 modules connected in series, limited only by the interconnection cabling constraints. The waveform you see here corresponds with 100 amperes under 66 kilovolts, that's which results in 660 kilowatts per branch. These tests confirm that the CHV converter can operate at high power levels. Regarding the dissemination, we elaborate two scientific papers. The first one was focused on the decentralized control CHV converter, has been accepted in the PCIM to present in June 2026, few months. And the second one was submitted in the ECCE conference. Both conferences are top-tier conference in the power electronics and energy conversion topics. In terms of technological impact, we demonstrate that the solid-state transformer can operate at high voltage applications, and we improve the solid-state module design and the decentralized CHV control converter architecture from the grid point. The project is helping to open a door to have a more resilient and smarter and more flexible grids. And finally, from the socio-economic perspective, the project supports the energy transition by enabling cleaner, more efficient, and more sustainable electric systems. Finally, lessons learned. Well, we demonstrate that the solid-state transformer can operate at high voltage operation, but scaling up is constrained by the insulation requirements which impact the final dimensions. The material and the design of the magnetic coil impact the losses, and the standard Ethernet does not meet the real-time requirements for the controller. Next steps: improving the magnetic circuit, rethinking the insulation solution, adding other deterministic communications, and scale up the solution. Thank you.
Good morning, all. My name is Elena from Rina Consulting, and today with me there is also Marikatia from CERT, and we will show you the results that we obtained from the sustainability assessment and potential study we did for the replication part of the STAR project. Today, I will explain the activities we did, mainly related to the environmental, the economic and social aspects we did for this project, and we will show you also the replication roadmap related to the TRL scaling up that we elaborated for this project. In particular, we will show you the life cycle assessment. We will show the technology acceptance study that we did through some questionnaire and survey, and we will show, as already said, the TRL scaling up at the very end of the project. I leave the floor to Marikatia to show you the activity she did.
Thank you, Elena. Hello, everyone. The life cycle assessment methodology was implemented to evaluate the environmental benefits of the proposed STAR pathways through all the life cycle stages. 1 kilowatt hour per 1 kilowatt hour of transferred electricity was used as a functional unit, and the system boundaries include energy and mass balances of the production, transportation, operation and maintenance, as well as end of life phase. The data derived from partners and filling gaps, also secondary data came from literature and also eco-event database of the CIMAPRO. Furthermore, all the environmental impacts were examined, and especially the climate change or else global warming potential, as well as resource use. And finally, the outcomes interpreted and come to very valuable conclusions. In STAR project, we have studied and evaluated 3 scenarios. The baseline scenario that assesses the environmental impacts of a conventional transformer, the STAR scenario that assesses the environmental impact of the STAR module, and the scale-up scenario that we have considered more than 1 module, actually 195 modules. Regarding the baseline scenario, we have data from literature review, and as the figure illustrates, we show the relationship between the global warming potential in terms of gram of CO2 equivalent per kilowatt hour transferred, and the nominal capacity of the transformers. In the first design picture, you can see the transformer that have a nominal capacity higher than 10,000 kilowatt hour, and in the second picture you can see transformer with capacity less than 1,000 kilovolt ampere. This revealed that we have a higher climate change with lower transformer capacity that give us an environmental burden. Regarding the STAR module, the main components of this was the IPT tank and PCBs. As you can see here, this module consists of individual parts that comprise of different materials, as you can see in the pie chart. It is interesting that steel and the electric fluid cover more than 74% of SST. The innovation material of one of the innovation materials is the bio-based the electric fluid that was assessed with different impact assessment methods. This shows us that there is no variety, there is no difference between the assessment methods, and so as the environmental performance have robust results. The outcomes of the life cycle assessment show us that the STAR bio-based fluid outperforms traditional mineral oils, and with a percentage difference ranging from 35 to 69%. It's highlighted that STAR bio-based the electric fluid also is competitive compared to other vegetable oils that used in transformers, and the environmental impacts fall within in the same order of magnitude. Also, it should be adhered that some differences can be attributed to different boundaries of the systems, elimination, and respective scalability. The the outcomes of the environmental impacts, and especially the climate change, you can see in these two pie charts. In the first one is illustrated the contribution of each phase of life cycle in the climate change when we use the European 2023 grid mix. And we can figure out that the electricity losses of the operational phase are the dominant contributor with 97% almost of the whole life cycle analysis, while the production phase is around 4%. However, it's highlighted that the negative, the impact of the end-of-life phase so was that minimize the environmental footprint, so can be attributed to the recycling of the materials. However, in case we use a reduced-based grid mix, also the operational phase is the major contributor. However, the production phase also represents a significant share, reflecting the embodied emission and the emission of the materials and the component manufacturing. The stage back to Elena. Thank you.
Thanks, Maria-Katia. Now we proceed with the social technology acceptance. We perform this activity with two parts. Our first questionnaire that we share internally with the consortium to understand a little bit better the use and the operational phase. We asked to answer to this question, in particular to the technical partners, because it was important for us to have their opinion. And then we prepare another survey that we share with external stakeholders to understand a little bit better how is perceived this new innovative technology to the common people, and to understand how it's seen from not technical, let's say, partners. Then we have analyzed also some use cases, because we found out that solid-state transformer developed in particular by STAR project could be used in different contexts, so from industry grid context to electric vehicle charging, but also to renewable energy sources like PV power plants and wind power plants, but also in data centers and utility scale energy storage systems. So solid-state transformer have different type of use cases and application. Going on the results that we did for the technology acceptance, we can state that there is interesting in this new technology. Of course, it's an emerging technology, so people would like to learn more about this technology, and for sure with STAR project we are trying also to do this. So also thanks to ICONS, who is the communication and dissemination part, we are organizing also this type of event to spread and to share the information related to the solid-state transformers. Going to the use cases, as I was mentioning, solid-state transformer could be used in industry grid connection concept, as like they are suitable for matches for medium and low voltages substation. They are also safe for indoor use. They are quite good at high temperature and high restricted environmental, which is something we focus a lot in the project. They are quite, they have this quite dynamic response to impulsive or cyclic loads, so they are suitable for motors, compressor, and other types of technologies. Moving on data center, that it was a topic that also was mentioned during the discussion before in the with the coordinator. We heard a lot about the data center in last years, and we found out that solid-state transformers are suitable also in this context, as they are digitally integrated power for this type of solution, and they are compliant with the regulation needed in particular for this type of the data center technologies. Finally, going to the roadmap, we built, let's say, all together this roadmap related to the TRL, which is the technology readiness level. It's composed by 9 levels, from 1 to 9. Actually, with STAR project, we are at TRL 4, which means we are in laboratory validation phase. So we tested the solution only in this laboratory phase, but we have started to think how we will reach the TRL 9 expected in 2030 as a full commercial deployment. For sure, we will need a prototype phase. After the laboratory, we will move to the prototype phase, and then moving forward, we will have the pilot deployment to test the solid-state transformer also in real grid condition, in real condition also from all aspects, environmental and all the aspects that we could consider, moving to the full commercial deployment with, of course, the large-scale installation of these solid-state transformers. Of course, I would like to mention that this, of course, is what we find out also analyzing all the literature aspects, and of course we hope that we will soon reach the TRL 9 and making possible the commercial deployment of this solution. It's all from my side, so I thank you all.
Okay, thanks to the partners. I would like to mention and to give thanks as well to our colleagues from ICONS, because they have been in charge since the beginning of the project of the communication and dissemination tasks. So it's crucial not only the technical partners, but also the transversal ones from the point of view of management as well, and the communication and dissemination aspects. So thank you for your commitment and your work during these months. Thanks a lot. Thank you to all the partners for the work, for the achievements. Okay, we are approaching to the official close of this project. So we have a lot of work to show. Okay, not only for, in this case, for the European Commission, but also for the rest of the people, as we have done today here. Thanks a lot for the people who attended today. Thanks as well to the people who is connected online. And I think that we are on time, so I don't know if there is some questions to our partners, to myself about the project, applications, future deployment, or wherever that you want to raise here before official closing and to have the catering. I don't know if there is some, yeah? conectarán de ahí, ahora, Eduardo.
So yeah, we have used an SPI communication between the modules, because remember that we are using hardware in the loop. So it's a perfect test bench to test the control without compromising money, and because we are dealing with this kind of developments are dealing with high voltage equipment. So if something fails, it's very expensive. So this kind of hardware in the loop system are very good for testing this development. And we have used SPI communication and also Ethernet communication but not for real time, only for management. But the real time communication in order to balance the voltage of the module is SPI.
Any other questions? The questions can be come from the technical point of view or another perspective. If you have some doubt about other European projects, real applications, how to integrate the sustainability in this kind of technology.
I don't know if you can say it like in public, but what is the difference between the price of the normal ones and the new ones? We can say what is. Or...
The price. The comparison price between the low frequency transformer and the SST. Well, there is, nowadays, there is the SSTs are becoming to the market, so it's not like a real comparison between markets, because the low frequency transformer are a very consolidated market. We have developed frequency transformer in UFASEC from a lot of years, and the SST is coming here, 75 years. And so I don't have like a market analysis itself, because there is no market, but I have been in a SIGRE consortium dealing with that question, and we have reached that the price could be between 4 and 5 times more than a low frequency transformer. So I think there is, if you want to change the low frequency transformer by an SST for the same application than low frequency transformer, I think there is no market there, because low frequency transformer works perfectly. But if you need more controllability, if you need to interchange the AC with DC, or exchange energy between DC generation and consumption in medium frequency, in medium voltage or high voltage, you need to go to this kind of application, you need to go to power electronic, and then there is a gap where SSTs can be a possibility. In fact, it has been added, it has been designed, the first SST, I will say, markedly available is for trains. So for mobility, or for data centers, or for medium voltage integration renewable, there is a gap there where in a few years could be an economic solution.
And maybe you have to make a real comparison in the same product, you have to add to the conventional transformer price the value of the system monitoring or something like that, to do something more or less. It's not the same, but it will. It's not only the transformer, all the sensors and all the system, monitoring system, and the communications with the dispatch or something like that.
Yeah, for me, it's like a comparison with the electric car with a combustion car. It offers different things. So a comparison directly with a low-frequency transformer, it's, from my point of view, of course, SST can do the low-frequency transformer things, but it's something else that a comparison in price directly has not too much sense from my point of view.
Okay, anyone else? Maria.
Why not? Here's a... Really? There's an echo. So here's the question. We have an IPT, okay? It has an echo. Like this? Dear God. Yeah, so we have an IPT, Inductive Power Transfer System, in the STAR project, okay? And the thing is that when you have an IPT, you usually have it like in EV charging, inductively, where you do not have one coil is in the vehicle, the other is on the station, many advantages there. But in this case, the architecture is that you put it in a box. It becomes like a solid-state transformer. It is not one part on the vehicle and the other. It is like all together. So what is the point? What is the concept between having an IPT not in a vehicle, but in a box?
In case of why are separated instead of having a very couple, it's because when our experience with dealing with medium and high frequency transformer, but for lower voltage application, that where there are no restriction for isolated onboard voltages, we have huge issues and challenge designing this medium frequency transformer because we have a lot of thermal issues with this medium frequency transformer without the isolation. We have burned a lot of transformers for that, so we know that the thermal issue, the thermal behavior of the transformer is an issue. So if you increase the voltage application and if you increase the coating, you increase the isolation material, it will decrease the capacity to transfer heat from the transformer, the dissipation. So, of course, the normal construction of transformers has their gap in order to build the SST, if this is what you mean. But for high voltage application, there will be, I think there will be a lot of issues with that, and with that solution, you can separate the isolation voltage, the isolation problem and the thermal problem in two parts, separately, more or less, or at least better than the normal design of transformers, which allow you to a better, in the long term, better reliability and lower problems. It is true that you can achieve, we are going to the details, you can achieve lower efficiency than normal construction transformers because are lower, has a lower coupling between primary and secondary, but the heat management is better. So where will be the point for this high voltage application? I think something in the middle could be, but.
Yeah, thank you. In fact, we were talking in the roundtable the crucial role of this kind of research technologies, social projects, in order to learn about this kind of barriers and how to overcome them. And this is the case for SSTAR. Now we know a little more about how to do it. And in fact, we have invested a lot of time in order to detect the right design of the modules in order to, yeah, you are blowing. Yeah, that's right. But finally, we have achieved it. Okay, we have found, independently of the size, weight, and whatever, that's something that must be implemented step by step to reach to the real market. Okay, but now, at least technically, we have identified the steps needed in order to get these technical results. So it's a key milestone for this kind of projects for the power electronics. So obviously, the next steps will be to identify solutions for this kind of lesson learned that we have shown here in these last slides. Okay, obviously there are a lot of things to think about, to increase the investment of this kind of projects in order to continue making this research and to have a real roadmap from TRL4, in this case for the STAR project, and we will see when we will be able to reach to the TRL9. We will see. Any other questions? Or suggestions, or doubts, or whatever? No? Okay, for the people who is connected online, you can contact directly to me. My email is available on SSTAR website. So if someone needs to ask something or to put in contact with us, I can maybe directly reply or forward the question to my colleagues based on the topic. Okay? So if there is no questions, let me again repeat thank you to all the partners for the work performed during these 46 months. I think that this has been a good commitment, a good collaboration, and a good coordination among us in order to put in common all the work to achieve all the initial objectives that we had at the initial stages of the project, when we were thinking if we will be able to complete the project as writing in the proposal. And now we have achieved this, and we have shown to everyone that we are capable to do it, and we will continue working, okay? So as you know, we are going to officially close the project, but we keep in touch during the next months, okay? We have to implement everything in several reports, okay, to be sent to the European Commission, and then to show the results to them, okay, and to our project officer. Thanks a lot. Thanks for attending, for the fruitful conversation, discussions that we have exchanged here, but we will have more opportunities to talk and to have more conversation later on, and obviously now during our catering, okay? So now it's time to enjoy in a different way, okay? We have enjoyed so far, I hope, and then we are going to enjoy in a different way with our catering and drinks, okay? Thanks a lot, thanks.